Thank you so much. Hi, everyone. We are Mountaineer PV Plus from West Virginia University. Thank you so much to all of you for being here. We're very excited to share our comprehensive solar plus storage design for New Mexico State University with you this evening. Like NMSU, West Virginia University is also a land-grant institution with a deep agricultural history, and we hope to take what we've learned in this competition to help shape the future of our campus as well. So we're gonna go ahead and make a few quick introductions. My name is Sam Talkington. I focus mostly on the power flow model and power system optimization.
My name is Morgan Kashon. I focus mostly on equipment selection and site design.
I'm Walker Gain. I perform financial and performance simulations in REOC Lite and System Advisor model.
And I am T. I functioned as the team lead and did a lot of financial modeling.
All right, so let me just start off with saying Mountaineer PV Plus was a team composed purely of undergraduates. We started with only a basic understanding of the processes and best practices of the solar plus storage development field, and this necessitated specialization among the members of our team. But this was a good thing because it enabled us to learn deeply, to focus, and to excel at one aspect of the project individually. And it also exposed us to the inherent multidisciplinary nature of this field. Whether we were working on the financials, the grid analysis, the site analysis, or the conceptual design, this was a fantastic opportunity for all of us to gain experience and learn as future solar professionals. So let's dive into some details. To drive our design, the Mountaineer PV Plus team utilized a broad stack of technical tools that we worked to integrate with one another seamlessly. While using Aurora Solar to enable us to bring our design's concept to life, our team simultaneously built a robust financial model using SAM and REOC Lite and optimized upon all of this iteratively. Of course, we then considered each iteration in regards to our site analysis, alignment with the master plan, and overall feasibility. But when it came to our distribution system impact analysis, we thought something was missing. We wanted to leverage our collective engineering background to enable us to make innovative design decisions that were not only efficient from an economic perspective, but also from a power systems analysis perspective through a grid optimization algorithm. So how did we accomplish this exactly? Well, we looked at industry and we realized that a commercially available software to find the optimal co-solution of PV sizing and siting doesn't really exist yet. So we designed a linear optimization algorithm ourselves, specifically for the NMSU circuit based on leading edge research in the power systems field. Not only was this one of the most innovative aspects of our design, but it was a great preparation for real work in this field. Our linear optimization algorithm relies on several key steps to help us make decisions. Firstly, a large amount of data is pulled from the inputted base case NMSU OpenDSS circuit provided by NREL, which is then used to define a series of constraints, like for instance, how many times a current overload can occur in a given year throughout the system. Finally, a series of objective functions that we want to minimize are defined, and they are iteratively evaluated across possible combinations of sizing and siting, i.e. how big and where our PV system is on the NMSU circuit. So we want to create a quantitative justification for how large a PV system should be and which buses to interconnect to on the NMSU circuit, shown to the left in our one-line diagram. To help us justify this decision, our team created the weighted heuristic function graphed to the right. This function works by evaluating the objective functions that we mentioned previously at each combination of PV size and interconnection site, plotted on the X and Y axes, and then those objective functions are combined into the weighted fuzzified heuristic or score plotted on the Z axis. Now, what exactly does an objective function mean here? Well, in the field of linear optimization, it's something you want to minimize or maximize. Now, for our system, our team decided our three key objective functions to minimize were real system power losses, the phase voltage unbalance rate, or PVUR, according to the IEEE definition, and the number of current overload events that occur throughout the year of operation. So again, we then weight and sum those objective functions at each combination of size and site. And then we find the maximum value of our heuristic or score. This value represents the optimal installation. And our model assumptions show that an installation range of 250 to 300 kilowatts of PV on the Corbett Center rooftop yields the most favorable power system impacts in terms of our objective functions. But interestingly, we can also see that there is a great deal of hosting capacity present on the geothermal substation bus due to the fact that the constraints are not violated at much larger system sizes. We chose to exploit this capacity due to financial benefits of a concentrated large system. Now, to talk more about our final system configurations, I'll turn it over to Morgan.
Thank you, Sam. So, as he mentioned, Corbett Center rooftop had an optimal hosting capacity of 250 to 300 kilowatts, and our final system design placed 278 kilowatts on the rooftop. And our second installation was along the geothermal road, and it totaled to 980 kilowatts, utilizing tracking. Both installations utilized equipment that was sourced from an approved vendor list for a real El Paso Electric RFP for a solar installation on New Mexico, excuse me. Both systems also utilize bifacial panels, choice motivated by the limited space on Corbett Center and the increased generation overall on the geothermal road field. The bifacial panels also work synergistically with the tracking implemented on the field, specifically with the NX Gemini tracker chosen, which is optimized for bifacial panels utilizing the two-in-portrait orientation as shown in the picture. The single-axis tracking also helps reduce soiling losses, which is something we considered as a potential issue in New Mexico. The final design for the substation field also included a battery installation, which I will turn it over to Walker to tell you more about.
Thank you. So our battery storage system was financially optimized through ReOpLite, which suggested to us a system with 405 kilowatts of power and a 4 megawatt hour capacity. We selected lithium iron phosphate batteries for their thermal stability and energy density. To the right, you can see a graph that shows a typical day of operations with the PV serving the load and charging our batteries in the midday to late afternoon, and the batteries discharging to shave off the peak power consumption in the evening. To make the most of our storage system, we explored leveraging several different revenue streams, including peak shaving, value obtained through resilience, and ancillary services such as frequency regulation and capacity firming. Through peak shaving operations, we found the university could save $50,000 per year in demand charges alone. In terms of resilience, our system can sustain critical loads for 2 hours on average and save $137,000 in lost operations for an outage of that length. And I want to reiterate that critical load was just for the buildings that we were given in the use case load data. Additionally, $60,000 per year can be saved through frequency regulation operations. So now that our system has been outlined, we can talk a little bit about the grid interactions. Using OpenDSS to validate our designs, we compared the results of each system iteration to the base case values. These results shown on the slide here reflect the final design values. So you can see the maximum and minimum voltage levels both expanded by less than 1%. The occurrence of voltage exceptions increased just less than 4% from the base case. And both current overloads and grid losses were reduced, which is in accordance with the objective functions that we outlined in our algorithm. Additionally, we expect that these results could be further improved using real controllers implemented in a different way. And now I'd like to pass it on to T, who will talk about the master plan and our design's accordance with it.
Thanks, Walker. So now that we've covered the systems, it's time to address our development plans. After reading over the master plan, we found this quote to be particularly interesting and also relatable to our own experiences on campus. Their master plan outlines a goal of creating mixed-use spaces outside fit for a variety of activities. To address this, we came up with an innovative solution combined with solar. This is a solar pergola we've designed with bifacial panels to create these kinds of spaces New Mexico State University wants. You can study here, eat your lunch, have a meeting with classmates or faculty, or just relax. We envision these pergolas to merge with the green landscapes and courtyard styling with yucca plant landscaping to add views and to create a sense of place in the Chihuahuan desert climate. This one is sited at the center of Hadley Hall Field, but it is meant to be a blueprint for the campus vision. They can be resized and sited elsewhere, fitting into the landscaping and courtyard designs throughout the campus, such as McPhee Circle, which is the new courtyard that replaced the parking lot west of Corbett. This design concludes every proposed system, so now we can look into the PPA and financials. Our final PPA price sits at 3.57 cents per kilowatt hour, escalating 2% per year. This is less expensive than their current levelized cost and provides energy that is safe from uncertainties in the energy market. From the P90 value, the system generates over 3 million kilowatt hours per year, exceeding 1/3 of their current consumption, which accounts for over 1,000 metric tons of CO2 saved compared to gas production. The financing model is a partnership flip, where the sponsor and tax equity will both see a 9% return. We aim to balance the benefits for all the stakeholders to ensure a successful buy-in for the project. The university will receive moderate bill savings of $80,000 over the lifetime, but even more from the value of added resiliency and impact to the campus vision, impression, and educational opportunities. Investors will receive their 9% return, which only takes 5 years to be made up for the tax equity. The utility receives solar credits at a 36% cheaper rate compared to their 2018 renewable portfolio standard, as well as frequency regulations from the battery, providing a very competitive bid for them. This is an overview of the financial flows with some key years noted. At first, since it's a partnership flip, the tax equity owns 95% of the holdings and sees its return through mostly the federal ITC and depreciation. Then at year 5, the ownership flips 99-1 for the sponsor, and they gain their revenue through the solar credit purchases contract and the PPA. There's also the option for NMSU to buy out the system, where if done at year 12, will net them $700,000 in life cycle benefit. We want to reiterate that these systems achieve a very competitive price. After removing the incentives and comparing this price to the Solar Energy Technology Office's Sunshot 2020 targets, this price is below the mark to reach market competitiveness with conventional electricity sources. So to conclude, our solution is a complete package that tackles the problems of planning solar and energy storage on a campus in an innovative way. We build up from the foundation, starting with optimizing the placement and sizes of the systems. Equipment is selected to make the most of our designs without sacrificing feasibility. The master plan is addressed combining 2 goals into 1 solution. And last, the financials offer every stakeholder incentive to support and buy-in for the project. We thank you for your time, and now we'll open up to questions.